This is Daniel Coosbury, and we're going to keep looking at geometry in this lecture. Most of this lecture is going to be me talking about things rather than doing a lot of problems. You're going to see we're going to look at polygons, and we'll do a perimeter problem, and then we'll talk about tessellations. So for starters, polygons are shapes that have corners, namely they're any sort of like closed figure that aren't circles, so they've got edges and corners. And here are some common ones. Here, and you're kind of familiar with some of these names. So a three-sided polygon is called a triangle, a four-sided is called a quadrilateral, and I'll let you read the rest of those. And one term kind of worth committing to memory is these are regular polygons, which means the word regular means that all of their sides are the same length and all of their angles are the same measure. So regular means they look exactly like what you're looking at. All these sides are the same length and all the angles are the same. So for example, a regular quadrilateral is just a square. All the angles are the same. They all happen to be 90 and all the side lengths are the same. So regular means same length, I can't write, and same angle measure. And so if I tell you I have a regular pentagon, you can assume that all 5 of these are the same and that all these 5 angles are the same. And that is going to help you do some problems in the future. These are some types of quadrilaterals. So most of these are not regular. In fact, so let's start with the regular one. So the square down here is regular because all 4 sides are the same and all 4 angles are the same. But we have some other ones that we've talked about. For example, a rectangle has opposite sides being the same length, and it also has 4 right angles. A rhombus is any quadrilateral with all 4 sides the same length. So there's no conditions on a rhombus as to what the angles need to be, so notice these aren't like all 90 degrees, but all these are the same length. So this is a rhombus, but it also means that a square is a rhombus because all 4 sides are the same. However, a rhombus can't be a square because the rhombus doesn't have those 90 degrees. So we have a few different specific qualities that you got to look out for to make these things. For example, a rectangle is any quadrilateral with 4 right angles and opposite sides matching. That means a square is a rectangle because it has 4 right angles and the opposite sides match. The special thing about the square is that all 4 sides match as well. And then we have a parallelogram, which has opposite sides being equal and opposite sides being parallel, and these opposite angles just happen to be equal. So we can use like this parallel sign here to note that these 2 segments are parallel. In the same way, we can kind of do a double arrow here to note that they're parallel with each other, and note that the opposite angles are parallel or equal to each other, which is really nice. The opposite sides are equal in length. And the last thing we have is a trapezoid, which has exactly 1 pair of parallel sides. So we can put arrows on those 2 sides to say they're parallel. And a trapezoid has some nice properties we'll look at in the next lecture. Okay, here's so perimeter. There's a lot of perimeter formulas. Basically, a perimeter is the distance around a figure. So I don't know if you really need a formula, but you do need to know what the lengths of all the sides are. So in some specific cases, here's a case where I have a rectangle, and I know that it is 400 feet long and 200 feet wide. Then I can use the fact that it's a rectangle to calculate the perimeter, because I know this side is the same as this side, it's 400 feet. This side is the same as this side, it's 200 feet. And but what I could also do is I could simplify that by just saying, oh, well, if I know the length, I'll just double it. And if I know the width, I'll just double it, and that gets me all 4 sides. Okay, so this problem says the fencing costs $14 per yard. What will it cost to put fencing around the playground? Now, before I actually do anything, I want to, well, no, I can do this first. I was going to note that we're dealing with per yard here, and we're working in feet, but I don't think we're going to get into trouble. We just need to do the conversion at some point. So let me do the perimeter. Perimeter is 2 times the length plus 2 times the width, which that's equal to 400 plus 800, which is 1,200 feet. I'm just adding up a bunch of feet, so my units are still in feet. But I'm looking at $14 per yard. So let's go ahead and change this to yards. So 1,200 feet. And for every 3 feet, we have 1 yard. That's a 1. So I'm going to do 1,200 divided by 3 to get 400 yards. And that's the perimeter of my playground. Now, I'll look back up here again, and it says it's going to cost $14 per yard to build this fence. So if I have 400 yards, and it's going to cost me $14 per yard, then using dimensional analysis, you can see my yards cancel, and I'm left with dollars as my unit. That's going to tell me how many dollars I'm going to have to spend on this fence, which is 5,600. So there you go. So what I did is I used the perimeter formula, and I got my perimeter in feet, and then I had to convert it to yards, and then I used that, or what it told me about how expensive the fence was, to calculate my final thing. I just turned that into kind of a unit fraction, $14 per yard. The yards canceled, and I got that. Okay, we're going to look at polygons and their angles a little more in depth now, and we're going to see how that kind of translates into tessellations. But you can kind of see in this this figure, it kind of seeks to generalize something we know pretty well. So what we know about triangles is that their angle sum equals 180. And we've already used that. If we have a triangle, we know that these 3 angles have to equal 180. So whatever they are, they add up to 180. And there's a formula we can use with bigger polygons that have more sides and more corners and whatnot by noting however many triangles we can divide these polygons into. It can kind of help us think about how many sets of 180 angles are there. So for example, here's a quadrilateral. I can split that into 2 triangles, which means this angle measure of this triangle is 180, this is 180, which means together it's twice that, which is 360. And I can do that with bigger polygons too. If I split this into 3 triangles, that's 3 sets of 180, which is 540, and so on. And I wouldn't worry so much about doing that yourself so much as realizing that's kind of where this comes from. So if I have a polygon with n sides, so that's my number of sides, pentagon n would be 5, hexagon n would be 6, then I can use this formula to tell you the angle measures, or the sum of all the angle measures in that polygon. So that's the formula we're going to use. And yeah, so here's a figure that's told us, we're told it's a regular hexagon, which means that all the sides are the same length and all the angles have the same measure. And it says, find the measure of angles A and B. So I want to find the angle measures of a regular hexagon, and I'm going to note, well, let me start by finding the sum of the angle measures, just to use this formula. So the formula is up here. Hexagon has 6 sides, so n is going to be 6. Plugging 6 into my formula, I get 4 times 180. Which is 720. So my total angle measure should be 720. Now I'm going to use the fact that this is a regular hexagon to note that all 6 of these angles need to be the same measure. And I'm going to use the fact that they all have to add up to be 720 degrees to get those angle measures. So if they all have to be the same and they all have to add up to this, that means I can divide this number by 6 to get each individual angle measure. So if I do 720 divided by 6, I get the angle of the measure of each angle. So what I just found out was that all these angle measures are 120 degrees. This is 120, this is 120, this is 120, this is 120, 120, and 120. So I used the fact that it was a regular hexagon to do that. I have this formula for the hexagon, and since it's regular, these all have to be the same, so I divided it by 6 to get this. And if you add these all up, they equal 120, so I did that right. So angle A, so the measure of angle A is equal to 120 degrees. And then angle B we can find now because notice this is a straight line, and it's got a segment coming out of here. So these are supplementary angles. They add up to be 180. So the measure of angle B is going to be equal to 60 degrees. You add those up, you get 180 degrees. So that's how I would do that. So there's certain advantages to knowing that you have a regular polygon, because that's what allowed us to take 720 and divide it by 6. Having a polygon at all, and knowing the number of sides, it's a hexagon, or just counting the number of sides, let us use this formula up here with the angles to do this. So that was kind of nice. Okay, tessellations. So tessellations are pretty fun to look at. What they are a bunch of regular polygons that are like copied onto each other or flipped or rotated and kind of stuck together so that they're repeated everywhere and there's no empty space. And so if you look at all these things, there's not any sort of empty space here. Even what looks like empty space here just turns out to be white regular triangles, and that was on purpose. So that turned out to be pretty cool. And so with certain regular polygons, you can make tessellations, which is kind of fun. And so one thing we're going to look at in particular with tessellations is that when you decide to make it, and the way you decide to make it, you've got to check that the sum of the measure of angles that come out at any one point is going to be 360 degrees. So here I'm looking at some regular octagons and some squares that are kind of left between them. And if I pick any point on here, any vertex, so like they're all pretty comparable to each other, but let's just look at this one. The angle measure all the way around here is equal to 360. That's just how it works. 360 degrees is one full rotation. That if I were to add up the angles that are formed at this vertex, I should get 360. Okay. So what this diagram has done is they found it's a regular octagon. So kind of like what we did with the hexagon example, we got 120 all the way around. That regular octagons have 135 all the way around. You can check that yourself if you want. So this angle is 135. This angle is 135. The square that's left over has angle measure 90. And if we add all three of those numbers up, plus 90, we get 360, which is good. This is exactly what we wanted. If we didn't get 360, we got something less, there'd be some white space that we didn't want there. If we had something more, then it would have been smushed together and our tessellation wouldn't have worked. So here's a nice little formula that we can kind of come up with that shows you how possible it is to make tessellation. So our condition is that if you look at any of these points or any of these vertices on here, the angles the angles that are formed at that vertex all need to add up to be 180. So if I were to put a little red dot in this first tessellation here, there's that red dot. If you were to add up those 6 angles that are made there, 1, 2, 3, 4, 5, 6, if you added those all up, they'd be 60. They'd all be 60. They'd add up to 360. Same here, if I were to just put a dot anywhere on any of these vertices in this middle one, those are 90, 90, 90, 90. That adds up to 360. So there's several polygons we can use to make tessellations, and we would check it by adding up the angles formed there and making sure it's 360. And there's a nice little formula here that makes things work. So I'm going to show you how to use this in a second. Okay, so this says explain why a tessellation cannot be formed using only regular pentagons. So pentagons n equals 5. And it's similar to those last examples where we had triangles and squares and hexagons. This is saying that we actually can't make tessellations with pentagons, and we're about to prove it. Okay, so let's start by finding the angle measure of these pentagons, each pentagon, if I were to make a tessellation with it. And I'm going to use this formula here that's given to me. It'll tell me the angle measures. I'm going to plug in 5. So 5 minus 2 times 180 divided by 5. This is equal to 3 times 180 divided by 5, which is, well, I'm doing that real quick. 3 times 180 divided by 5 is equal to 108. So if I were to make a tessellation, or to try to make a tessellation with pentagons, the angle measures would be 108 degrees. Let me see if I can kind of draw this so you know what I'm getting at. So if I were to do a regular pentagon, and that's my best attempt to draw a regular pentagon, then it would kind of look like that. I'm not very good at this. 1, 2, 3, 4, 5. Okay, so those are 3 pentagons. They're supposed to be regular, but what I'm saying is if I were to do this, I get 108, 108, and 108. And there's going to be some extra space here. It's not going to add up perfectly to 360. So that is to say if I were to add 108 plus 108 plus 108, I would get 324, which is not quite 360. And if I were to add another pentagon here, I wouldn't be able to fit another 108 here. And so all this is to say I don't have a nice thing like on this slide where I add up all those angles that are the equal angles and I end up with 360. What I have instead is I have these angles, which have to be the angles, the proper angles in the pentagon, and I don't get 360, and if I throw another one in there, I get more than 360, so this is bad, and this means that I can't make a tessellation with pentagons. And so if given a question like this, explain why you can't make a tessellation with a certain regular figure, you would use this formula to find the measures of each angle, and then you would show that you can't add enough of those together to get 360. You either come up short, you're going to be above it. You're just not going to be perfect like in these examples where you added them up and you got 360. So that's how I would explain that.